Hi everyone, thank you for coming my talk and thank you for giving me a great opportunity to speak to talk about my recent study about the, our new original method for the risk assessment of induced seismicity. I think I don't have to emphasize the importance of the issue of induced seismicity, so I just start from here. Okay, this is just an example of the research on induced seismicity, which is related to the geothermal development. So you can see that many scientists and many groups studied for the induced seismicity with various approaches. But I understand our common goal is investigation of the physics behind the large induced seismicity in the point of science. And in more practically, we need to develop the risk assessment method or the techniques of the software stimulation. I and my group have been studying for the induced seismicity with large magnitude for the geothermal development. But unfortunately, we haven't reached the clear understanding of the physics so far. And the other major approach is statistic-based approaches. So, but our previous approach is really based on a physics-based one. So we think we need the other risk assessment method based on clear physical meaning, based on the microseismic datasets. And what we realized this is a recent progress of microseismic monitoring techniques and analysis method. I'm not sure actually about the recent microseismic monitoring about the analysis method, but I know that now we have a really good data set, and we can do this, or we can do hypocenter determination and the estimation of magnitude and fault area and the fault plane solution in semi-real time. So why we don't use it? So we try to use it, and using this information, we try to establish some development. We try to establish some risk assessment method with clear physical meaning. So this is what I want to propose you, our model, named slipped able area. Okay, you can see the really simple model. This is described by the simple multiply by the potential slip able area density and stimulated rock volume. I will explain about that in detail, but I try to explain about the characteristics of a model. So slip-able area model is completely based on the microseismic information, and the output is a cumulative fault area. So the physical meaning is really clear. And the fault area can be translated into the magnitude of the seismicity, maximum magnitude of the seismicity. And this model is designed to use a result of analysis, semi-real-time analysis. So this can be evaluated almost in semi-real time. I'll show you some example. Okay, this is some example of the cumulative fault area, and which is a function of time. A red line is estimated by the observational data. And if I put some model output, so in this case, model output is larger than the observed value, so which means a high seismic value, high seismic risk. Because this differences means there are many slip-able faults in future. Okay, in the case of the model is lower than the observed value, so which means a low seismic risk, because there are not so many slip-able area, and moreover, we need this model should be adjusted, because in my model, the best condition is observed value, and the model one is completely matched. So in order to estimate the slip-able area, we have to estimate a K value, a potential slip-able area density. Okay, now you have a sample area in a study area. I mean the geothermal or some reservoir. And now there should be some existing fault like this, but there is no practical method to measure how large and how many existing faults. But during the stimulation, some of them have a shear slip like this, and you have a microseism. So you can estimate the fault plane of the fault area of these microseismic events. And this is an observational fact. So now you calculate a summation of these slipped fault area, then divided by the volume of sample area. So now you have a K value. That is a potential slip-able area density. Okay, the other parameter is stimulated rock volume. I call the V stimulated in this presentation. This is also based on information of microseismic events, time-space migration of microseismic events. Okay, here we separated the reservoir into using some unit grids, and then just count the number of the grid, including at least one microseismic event. Then just calculate the number and the unit volume of unit grid. Now you have a stimulated rock volume. So now we calculate these two values, and you have a slip-able area. So that meaning is cumulative fault area under the critical state. Okay, I would like to make sure about how to use this model. Okay, as I talk about, K value is estimated from the occurrence time hypocenter fault area of the microseismic information. So K value is kind of a sampled value. And if you have maybe this kind of time series of K value, so each time step you can calculate at K value like this. And we have a big assumption here. K value is homogeneously distributed all over the reservoir. But K value can change by the time steps. And then we have to also calculate with stimulated like this. Okay, now we have the time step 1, time step 2 with stimulated area. As I explained, the V stimulated is calculated from the distribution of hypocenter of microseismic events. But in order to forecast the seismic activity in future, we have to forecast the V stimulated. This is also the big hypothesis in this model. So now we estimate V stimulated in time step 3 from these value, something like this. Yeah, and then we have actual data. And for the next step, we also calculate from this value and this value. And now we have V stimulated area in future, and then, and then, and then. And finally, we have this kind of slip-able area. Okay, so just I show you some example. For the slip-able area in time step 3, you have to use the K value of the time step 2 and just forecasted V stimulated area in time step 3. So just forecast value. So now we have a stimulated slip-able area. This can be convertible to the magnitude and seismic energy at each time steps. Okay, so I'm changing my talking to the application to the real microseismic dataset. I just tried to apply this model into the microseismic dataset from the Basel. I skipped the detail of the Basel, but our group have been determined the precise hypocenter rotation like this, and also I have estimated some fault area like this. Okay, this is a result of first estimation of slip-able area. Okay, top figure shows a hydraulic record, and the next one is magnitude history, and the bottom figure shows a result of estimates of slip-able area. Black dot shows observed fault area, so that's the actual dataset. And the red one is a slip wave area. And in this case, I use a 14 meter of grid to estimate a V stimulated, and 20 meters cubic to estimate a K value. So maybe you can see the slip wave area showed here is really good fit with the observed fault area. This is kind of serendipity, but really happy. I'm really so happy. But this indicates homogeneously distributed existing fracture sample, I mean the K value, and the volume based on the microseismic distribution, I mean the V stimulated, presented heterogeneously distributed for the plane of the large events and the microseismic events. And this trial shows some possibility to forecast the scale of the future seismicity when K and V stimulated can be applied estimated. And I want to make sure here, actually, in this trial, I don't forecast the V stimulated. I just use actual data. So we need to develop some method to estimate, to forecast the V stimulated. That's my future work. And conclusions. We originally proposed a risk assessment model named slip wave area, showing described by this simple equation for induced seismicity based on the variation of the fault area under slip wave conditions. Estimates of slip wave area using microseismic data set from Basel show the significant consistency with the summation of the observed fault area. So this shows some possibility to predict some scale of seismicity in near future, and when we have, of course, when we have appropriate parameter can be estimated. And this model also have some room to extended. This is extended of slip wave area. So the equation becomes a little complex. So we can put some more physical based parameter like a stress state of the fracture plane into the K value, or distance from the feeder point into the K and V value, something like that. So we have this model is going to be more realistic model. That's it. Thank you.
Do you have questions?
Yeah. I was wondering, you said before when you had your observed model, your observed versus the model, and if your observed was below what your model was, you would perhaps try and fix it so that they both met up with each other. I'm just wondering what types of corrections would you apply to your model to make it better fit your observed?
Actually, we don't use a question.
Repeat the question. Please repeat the question.
Oh, okay, I know. Could you tell me his question briefly?
The question?
Yes.
Could you repeat the question?
Yeah, could you repeat the question briefly?
I was just wondering, you said when you have a difference between, in your model, between what you had the curve that was the observed and the curve that was the model, and you said at points you would try and correct the, do a correction for it to make them fit each other. I was wondering what kind of corrections you would apply.
This one?
No, back. Back. Yes, right there. When you said like when you had the low seismic risk, you said the model should be adjusted. How would you adjust it?
Yeah, okay. So my model has some several scenario. So here I just use it's kind of how to determine the K value. So I just use a K value. I just select some grid which has a maximum number of microseismic events. and then estimate the k-value. But if you change how to select the grid to calculate the k-value, you can change the k-value, so you should change the other result.